So this chapter deals with properties, thermodynamic properties, and one of the most common fluids that we have to deal with is water. And so if you take a look at a lot of the tables, A2, A3, A4, A5, A6, they all deal with water, 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 water. And so we want to get into our mind, why do they have so many tables for water? Well, you can look at the title of the table and help you understand. So this is saturated water. It's where it's that two-phase liquid vapor mixture. Think about the dome on the PVT surface. And temperature is the primary input, or pressure is the most convenient primary input. That's why they have it both ways. And in the two-phase region, the saturation pressure is a function of temperature. They're not independent. Or you can say the saturation temperature is a function of pressure. Either way. So P is a function of T, or T is a function of P. They're not independent properties. But then you move out into the superheated. And a lot of times in power plants we make superheated vapor. And so it's not saturated vapor, it's well into the superheated region, meaning it's not close to condensing. You'll have to cool it to get it near to condense it. So that's superheated water vapor. Then the other is compressed liquid. You can think of liquid where it's below the saturation temperature, and they do have a table for that properties for water for a saturated liquid or compressed liquid. Either subcooled liquid they'll call it, or compressed liquid. And then they also have one for the saturation region where it's a solid vapor mixture. So if you take a look, there's 1, 2, 3, 4, 5 tables for water, but when you look at refrigerant, the refrigerants, here's refrigerant 22. How many do they have? Only 3 tables. How about refrigerant 134A? Only 3 tables. Well, similarly for other refrigerants, they don't have as many tables. You'll have to use approximations or other ways. But the most data that you have is for water in the back of the textbook. There's a lot of data on this table. Last time we covered it. What is the starting point for table A2? What is that first entry? And what's the very last entry? One is the critical, one is the triple. So what's the first entry? Triple point. And the last one? Critical point. All right. And we did talk about this factor 10 to the 3. You need to, if you wanted to get the specific volume, let's say at 100, it would be 0.0010435 meters cubed per kilogram for saturated liquid. Also, we talked about the energy. Where did the energy measurement start for water? Saturated liquid at the triple point, internal energy picked to be 0. And then you just make measurements from there. So you can get, in the next table we will see, negative values for internal energy and negative values for enthalpy. Why? Well, because you have to remove energy, decrease U or decrease H to get to that low temperature. Hence, you get a negative internal energy. So again, that reference state, when you make energy calculations, it's really only the change in U that's important. It's not the value of U. Okay, so there it is. Also, the extra column over here, enthalpy has 3 columns: internal energy 2, specific volume 2, entropy 2. Why 3? Well, the extra column is not saturated liquid, not saturated vapor, but vaporization, evaporation. It's HFG is H of G minus H of F by definition. You just take these 2 numbers, that one, subtract that one, you'll get this one. Well, That's not new information, is it? No, it's just handy information, and hence it's so handy they put an extra column in there. If you can kind of remember that, you'll see why they do that for enthalpy. When you get to Thermo 2, why do they introduce a new property called availability or exergy? It's just convenient. It's just convenient. So this new enthalpy, you can think about what does it take in a constant pressure heating process to start a system that has, let's say, the weight of the piston, and you start with saturated liquid, and you add some heat, and so the final state, you'll have a lot of expansion, so we'll show the piston way up there, and here it's saturated vapor. The elevation of that piston has changed. The volume has changed, but it did the pressure final, is that equal to the pressure initial? If this is state 1 and that's state 2? Yes. You just draw a free body diagram of that piston and elevation doesn't come into play. Okay, so P1 is equal to T2. That's how you have a constant pressure heating process that goes from saturated liquid to saturated vapor. If the focus of the analysis is that trapped amount of fluid, and we say, let's do a first law analysis of this system, right? Conservation of energy, what would that equation look like? It'd be how much heat is brought in to the system during the process minus the work done by the system as it expands and pushes up that piston, equal to the mass times the change in internal energy plus the change in kinetic energy plus the change in potential energy. Did I write the first law okay? Could you write that from memory? Hopefully good. So in this problem, what do you think about change in kinetic potential energy? Negligible. All right. What about the boundary work? Is that boundary work 1 to 2? Is that work 1 to 2? Is that the integral of P dV? Can that pressure come outside the integral? And why? Because it's constant. And so this work becomes P times V2 minus V1. Is that true? We could write that as P2 V2 because P1 is P2 is the same pressure minus P1 V1. That's fine. That looks good. And so what we have is the amount of heat that has to be added to the system is equal to the mass times U2 minus U1, and we'll bring that work over, and so we'll have the work. This is, if I want to do the integral P cap V, that's great. If I want to do specific volume, then I need to multiply by the mass. Let me tuck the mass in there. And the mass right there, and then the mass right there. Now finally I'll have plus P2 V2 minus P1 V1. I'm just taking this term and putting it over on the other side when we express it as constant pressure work. And so now we're going to get the mass times H2 plus P2 V2 minus H1 plus P1 V1. And what do we call this new property, H? Enthalpy. It's just a convenient new grouping of terms. It's defined as, a lot of times mathematicians will put 3 on that equal sign, right? 3 strokes instead of 2 on that equal sign, saying this is defined as U plus PV. That new property is conveniently tabulated. You can go back and check, grab some random numbers in the textbook and see if, sure, if I take, let's go back here. Let's just say, is H of F right here, is that 20.9? Is that equal to the internal energy, U sub F, plus the pressure times the specific volume, chase your units, it will be precisely the same. So why did they just repeat numbers in the textbook? Well, because this is a convenient property to have known as the enthalpy. And when we have constant pressure heating, we find that cap Q is equal to the mass times the change in the enthalpy, final enthalpy minus initial enthalpy. If you're starting with saturated liquid, H of F, and going to saturated vapor, H of G, then it's just the mass times HFG, the heat of vaporization, that middle column. So it's real convenient. If I have constant pressure boiling and I have so many kilograms of water that comes in saturated liquid, I want to make saturated vapor, that's how much heat has to be added.
When we separate the variables into two states, we say two.
Yeah, I needed that mass right there on this cap W term.
No, the two lines below it.
Okay.
After the
Uh-huh.
1, 2.
Oh, yeah, this is messed up. That's a U2 and a U1. Thank you very much for the typo fix.
Instead of internal energy, correct?
Yeah, so this becomes H2 minus H1 times the M. So Q1 to 2, I kind of rewrote it right up here. Yeah. Okay, so now let's press forward. So this one I did last time, did I not? But I cleaned it up a little bit. We start with water at a low temperature, negative 40. What is the state of water at negative 40 degrees C? Don't leave this class without being able to answer a question like that. It's a solid, it's ice. And then if you pump some heat in, it'll warm up, it'll finally get up to 0. You pump in more heat, it'll go from saturated ice, like the solid, to the saturated liquid. This what's happening right in here, melting. And so anywhere in here you have a two-phase mixture of solid liquid in equilibrium. But once it's all liquid, you keep pumping in heat. Now the temperature is going to rise, and it gets up to another magic number that is 100 degrees C, we recall. That's the boiling point. Now it's saturated what? Liquid, meaning if I add any more heat, some of it's going to start turning into vapor. And as I add more heat, more of it turns into vapor until it's all saturated vapor. But the temperature didn't change. At constant pressure, 1 bar, or 1 atmosphere, it's at 100 degrees C. It's the boiling point. This is something that throws students for a loop. They can't figure that out. They'll make the mistake conceptually. What happened? And, the temperature stayed the same. Well, then you couldn't have added heat. If you added heat into it, the temperature is going to go up. Not if it's changing phase. Not if you're either boiling it or melting it. Anyway, once it's saturated vapor, you continue to heat it, the temperature goes up, and you get superheated vapor. You can get the specific heats, and the heats of melting and the heat of boiling or heat of vaporization. There the numbers are. Well, the next one is the pressure table. So if pressure is the most convenient input parameter, and you know it's a two-phase liquid vapor mixture of water, you can use the pressure input to get, let's say, U's or H's or V's. It's probably not as well used as the previous table A2, but it still can be used and is used. So we talked about table A2 and table A3. What's the next one? 4. Superheated water vapor. Where is it on our pressure temperature diagram? Well, remind me, we had the critical point, triple point. We had lines separating the liquid region from the vapor region. We had a line, saturation state, separating the liquid and the solid region. A line, saturation region, separating the solid from the vapor region. Okay, that's a good reminder. Okay, this is my PT diagram. Well, vapor that's far away from the saturated vapor. Either it's saturated vapor close to liquefying, or down in here it's less common, but you could have saturated vapor that's ready to be deposited into a solid, or the opposite, sublimation, boiling. But anyway, this would be superheated vapor. Now, right away, I'm going to say that a significant portion of this superheated vapor region does behave as an ideal gas, even for water. But until you're really good at it, don't assume it can behave as an ideal gas and can be treated as an ideal gas. Treat it like I need to go and get the properties out of the table. Because every now and then we'll say, well, I could treat water sometimes in this vapor state as an ideal gas, so I'll just extend that into the liquid state. And I've seen it. Students using the ideal gas equation, two-phase mixture, most of it's liquid, and the way they go. Well, they got some numbers, but their answers are wrong, right? Okay, but we're going to talk about ideal gases later. It's a portion of this superheated vapor region. But we can get data out of the table for superheated water vapor. Then just they're showing you that by this little grid. They're showing you as a function of temperature and a function of pressure. You can get data points, all right, from the table. Likewise up here, for the compressed liquid table, in the liquid region, there's some data points. All right. And then the last table, A6, look at the title, Saturated Water, Solid Vapor, Temperature Input, or Temperature Table. Where on this PT diagram is data from table A7? Where is that at? It's right on this line. That's right. So it's below, oh, I forgot the name of this point. What's the name of this point? The triple point. Okay, so where's data A2 on this plot? Just on this line right here between the triple point to the critical point. How about the data table A3? Same. It's just whether or not you're coming in with pressure known and you're interested in temperature and other properties as a function of pressure, or you're coming in with temperature known and you're getting pressure as well as other properties. So let's take a look at the superheated table. Well, how do you get into it? Well, it's in pressure blocks. So all of this data right here is for the pressure block of 0.7 bar. Here's one for 1 bar. And then next index is temperature. It goes from the lowest temperature. Why did they put the letters SAT for the lowest temperature? Why didn't they tell me the numeric value of the saturation temperature? They did. They just put it right here. So the saturation temperature is 89.95 degrees C at 0.7 bar. And then 100, then 120, then 160. So here is your value of V, U, H, and S. How come they don't have, H of F or use of F and use of G? I mean, why don't they have two entries? There's no longer a quality. It's superheated vapor. It's beyond. So sometimes students will try and calculate a quality in the superheated region. They'll get a number of about, 1.3. There's no quality. Quality is only used from saturated liquid to saturated vapor. If you're starting to get qualities below 0 or above 1, look for an error. Okay? Now, interesting, you can extrapolate out into the superheated region and maybe get a quality 1.05, and that'll actually give you a pretty good number, close to the real number. So it won't be off much, but just don't do it. Don't ever have a quality greater than 100%. Okay, so these are all for the values of the at that temperature and pressure. This is one of those convenient things where temperature and pressure are two independent intensive properties, and basically that's the way we fix the state. If you wanted U, you'd get it as a function of pressure temperature. Get to the right pressure block, then to the right temperature line. H the same way, V the same way, S the same way. How about the next table? Compressed liquid. Guess what? It's in a pressure block. But the pressure block, look at the magnitude, 25 bar, 50 bar. There's not that many, and they have huge, pressure changes between them. And then here are the temperatures. What does this saturation mean? Yeah. So if you're at 25 bar, it's going to have a boiling point of 224 degrees C. Pretty hot. But under high pressure, it'll have a higher boiling point. And then the solid vapor mixture of water is saturated water. And a couple things to notice. What is the starting point? The highest temperature, triple point, and then you go low, 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 cold, cold, cold. And take a look at the values of these U's. They're low. And so they're negative, okay? So it's that negative energy. What was our reference point? It wasn't use of G at the triple point. It wasn't use of ice at the triple point. It was use of F was set to be 0 at the triple point for water. Okay, that's why it's so negative. Okay. What is the state of water? 10 bar and 240 degrees C. First of all, make sure that you're in the water table. How many times somebody will be over in the propane, or they'll be in the R134A table, and they're looking for water properties, and they have a problem. So make sure that you're in the water table, one of the many water tables. And so who's a brave soul wants to tell me the logic? Okay, but you have to explain the logic. Go ahead and explain the logic.
I got vapor because on the pressure table, I went to 10 bar and I looked at the temperature.
So you went to table A3 because the pressure, 10 bar will seem to be an index. And you went down that line of 10 bar until you found? So you found the saturation temperature at 10 bar to be 179.9 degrees C.
And it was over that, so I concluded it was vapor.
Then he made an excellent comparison of that 240 is the actual temperature. The saturation temperature is 180-ish. It's over it. It's larger. It has to be superheated vapor. Has to be superheated vapor. What happens if they change it and they say it's 40 degrees C? What do you think? If it's 40 degrees C, same 10 bar? Liquid. Liquid, yeah. Let's say that it was 179.9 degrees C and 10 bar. Liquid vapor mixture. It could be mostly liquid, mostly vapor, but we know we're in the where it's saturation. Liquid vapor saturated mixture. All right, what is the internal energy, that's lowercase u, of water at 10 bar and 240 degrees C? Well, we already looked it up. We have to go to the superheated tables now, right? So if you flip to the superheated table, you find your 10 bar block. And at the 10 bar block, you go down to 240 degrees C, and you read off U. Anybody have a number for that? C, right? So just make sure you can do that. If you can bring your tables next time, for sure. Just because we're making this whole chapter is on getting data. There's more of these. Let me skip them. More of these. Let me skip them. Not because they're not important, but really watching me do it's hardly helpful. You've got to do it. All right, this one we'll do. What is the lowercase u? What's the name of that? What's the name of lowercase u? Specific internal energy for the fluid water. So let's make sure we're in the water table. 6 kilopascal and 50 degrees C. If you go and compute the saturation table or look it up, saturation temperature at 6 kilopascal, you'll find that it's 36.16 degrees C. The actual temperature is greater, hence it's superheated. We go to the superheated table, and here we are, we're at the right pressure block. And we're going to come down to 50 degrees C, but I don't see it. So what do? You have to interpolate. And what number the temperature for this first line? 36.16 degrees C. So we need it between these two values right there. What I like to do, especially I recommend you do, is take your time when you're learning how to do the interpolation and getting data out of the tables and make a subset. So think of temperature, 36.16, here's degrees C, so you don't have to repeat it, and 80.00, and then over here U in kilojoules per kilogram. So we'll pick off the 2425.0, and then we'll pick off the 2487.3. And I know I'm doing the interpolation, so I leave a little bit of room here, and I put 50.0. And then I draw an arrow. This is the way I do it. And then I say, this is the number I'm looking for. Okay? And when I'm brand new to this, I may even make a plot, because I remember how to do y as a function of x. And I have x1, y1, that's a point. And I have x2, y2, and that's a point. Well, I didn't draw it too well. And then I think of any point in between. So given any x between x1 and x2, I can easily get y. It's the same fraction, isn't it? So if I move 10% from x1 toward x2, that would be like x minus x1 divided by x2 minus x1. It's how far am I moving in the numerator from x1 toward x2 divided by the total travel distance between x1 to x2. That's some sort of fraction. This is some fraction. Okay, if I'm bringing in an x that's between 1 and 2, and I compute this, and I don't have a fraction that's between 0 and 1, I have an error. So this fraction is 0 to 1, and that's equal to y minus y1 divided by y2 minus y1. Isn't that the equation we use? In general, how many people remember this, learning it this way? Yeah. So you tie into your previous knowledge and you build on it so you avoid making a mistake. So that here what we're going to have is not x as an input. This time it's temperature as an input. Not y as an output, but U, internal energy, as an output. So it'll be that T minus 36.16 divided by 80 minus 36.16 is equal to my desired U minus the U1, 2425.0, divided by 2487.3 minus 2425.0. Did I do that okay? And then now I put in my numeric value of 50, and I have it. Make sure you can do interpolating and getting the data out of the tables. And then when I put a number back in here, if I have like 2397, guess what? I have an error. It's going to be between these two values. Let's say I have 2879. I have an error. I look for my error, okay? All right. Those are the best hints I can give you on avoiding errors. double interpolation. Professor, this is so old school. Yeah, but it's so easy. Come on, linear interpolation. It's easy. Double interpolation, just as easy. And you might anticipate a problem where you need to do double interpolation. Here's an example. I need the internal energy at 20 kilopascal and 95 degrees C. So I determined that at superheated vapor. So I go into the tables and I'm looking for a table that's 95, well, first of all, 20 kilopascal. This here is 60 kilopascal, and this is 350 kilopascal. No, it's not 350. It's, sorry. This is 6 kilopascal and 35 kilopascal. Okay? So 20 is in between. And then the next one is 95 degrees C. Well, you can tell it's not on the temperature line either. So what do I do here is I make an additional new table where it's at 20 kilopascal, whatever, however your mind works. You interpolate with respect to one first, one of those variables, pressure or temperature. So at 20 kilopascal, I want to make one value of U at both 80 and 120 degrees. So I do a linear interpolation with respect to pressure to get a U at 80 and a U at 120. Once I have that, then I do an interpolation with respect to temperature to get it at 95. A little bit of work, but can you do it? Make sure you can do double interpolation. Any questions on that? What is the difference between a subcooled liquid and a compressed liquid? Well, what's the similarity? Both of them have the word liquid in it. But this qualifier, subcooled, meaning it's not saturated, and this qualifier is compressed. Compressed has an idea of pressure. Subcooled has an idea of temperature. So a subcooled liquid would mean that the actual temperature is less than the saturation temperature. That's what it means. What about compressed liquid? That the actual pressure is greater than the saturation pressure. Does that make sense? But if you have both of these conditions, it's liquid. It's liquid. So now let's take a look. Subcooled liquid has a temperature below the saturation temperature. Yeah, we'll give that a thumbs up, but there's a comma, there's another part to the statement. While the compressed liquid has a temperature greater than the saturation temperature. What do you think about that statement? If your temperature is greater than saturation temperature, you do not have a liquid. So this statement's not good because of the second half. Compressed liquid with a pressure greater than the saturation pressure, that's good. While the subcooled liquid has a pressure less than the saturation pressure. Hold it. How can you have... No, this makes no sense. Subcooled liquid has a temperature greater than the saturation temperature. If it's greater than, it's not a liquid. No, that's no good. Compressed liquid has a pressure less than. No, that's no good. None of the above. You need both of those. But what's the difference? It's just name calling. That's all it is. If somebody says that if I tell you it's a compressed liquid, I'm also telling you it's a subcooled liquid. They're describing that it's a liquid that is not close to the saturation state. All right. Sometimes we need to make approximations for subcooled liquids or compressed liquids. Name calling is that. So here it is. If you don't have a table, just say that, well, I'm looking for the specific volume as a function of temperature and pressure. The approximation, meaning it's not precise, but it's a very good approximation in most cases, is that you'll use the V sub F as a function of T. So this is the math, as the equation as it's written. But what does the F subscript on that V mean? What does the F subscript mean? Saturated liquid. So even though it's subcooled, we're going to neglect and we're going to get a value for the saturated liquid and use it. But what are we going to neglect? We have a temperature input and a pressure input. Did we neglect the temperature or neglect the pressure? We neglected the pressure. So when you're using this approximation for a subcooled liquid, sometimes the student will use V sub F at the given pressure. They'll take that pressure and put it in and then get V sub F. Guess what? You'll get a different answer, and it's not the best answer. The best answer is to neglect the effect of pressure. Why do you neglect the effect of pressure for these liquids? Because liquids are nearly incompressible. So if I boost the pressure, it really doesn't change the property. It's incompressible. But it could have a slight temperature dependence for the density or specific volume, and definitely for the enthalpy and internal energy. So for all three of these approximations, basically you're neglecting the pressure. There's a problem. Let's skip it. Another problem. Let's skip it. Another problem. There's a lot of problems. So you have to be working problems. How many people worked a lot of problems? Keep raising that hand every time I ask a question, because you need to work a lot of problems. Let's go to another one. Well, can't find it. Let's talk about refrigerants. So the next three tables are dealing with R22. Then the next three tables deal with R134A. The next three tables deal with ammonia, NH3. The next three tables deal with propane, was that C3H8. And so those are all used in vapor compression refrigeration systems. Okay, which one is more common? 134A. How many people know if they have an automobile and has an air conditioning system in it, what's the refrigerant in the automobile air conditioning system? 134A. How many people have an old residential, let's say older than 5 years or so? It's probably R22. If you have a more modern residential air conditioning system, it's probably 410. Right. Ammonia is used in large plants for refrigerant. And propane is used more exotic applications. It's not as heavily used, but can be used as refrigerant. So you have the temperature coming in for the saturation table for the refrigerants, and this is for the 134A, this is for the ammonia. Let's take a quick look. What is the lowest value of temperature in the 134A? -40 C. How cold is that? Very cold. But sometimes you have a refrigeration application that wants to get something to -10 degrees, -20 degrees C. So they put the temperature pretty low in the tables. Okay, what else do you observe? Where is a value of 0 for the energy datum point, for the starting of the energy measurements? It's saturated liquids enthalpy is set to 0 at -40 degrees C. Is that true for the ammonia table as well? Well, here's -40. It's not the lowest temperature. But what is the H of F, the saturated liquid enthalpy at -40? So refrigerants are pretty consistent. They set the datum point for the energy as the internal energy of saturated enthalpy of liquid at negative 40 to be 0. Do you see some negative values of U? Sure. That's a consequence of having the value set to 0 somewhere else. If you get it colder, you'll have lower and hence negative numbers for the internal energy. Now this will throw you for a loop later. Because you pick a datum point, you can have a negative entropy. I'll emphasize that when we get to the second law. It's just always a change in the value that's important for energy and entropy concepts. All right. We already covered that. You use this approximation more in the refrigerants because you have fewer tables for the refrigerants. Should we solve a problem or move on? Solve it? So we have propane. It's initially saturated vapor at a given pressure, and it's in a rigid tank. How many times, if you were brand new to this problem, would you reread that first line? At least 5 times. Because you want to understand, okay, it's propane. It's initially saturated vapor. They tell me the pressure, and they tell me something about this tank that's containing it. What is probably the most important key word that's brand new to you? It's that rigid, R-I-G-I-D. What does rigid mean? The volume is not going to change. The volume is not going to change. The propane is heated until the pressure is 600 kilo. During the heating process, did the tank size change? Nope. It stayed rigid. It stayed the same volume. Did the pressure go up? What do you suspect the temperature did? It probably went up. It was heated. You suspect it went up, and you're pretty good at suspecting those things. And yeah, you're going to show that it would go up. Changes in kinetic and potential energy are negligible. For the propane, show the process on a pressure volume diagram. I think you need to do that, so let me pause and walk around and see if you can show me on a PV diagram what this process looks like. So let's go ahead and put a generic pressure volume diagram. Is that the right way to put it? Put P on the y-axis, V on the x. And then we know that it's pretty steep, gets up to a point, and then it kicks way over. But people could draw it symmetric, it'd be okay. What's at the top of this PV diagram? CP, the critical point. And every state off to this side, coming down on the right, is a state of saturated vapor. Every point coming off on the left, on this line of the dome, from the critical point on down, is saturated liquid. So we are starting with saturated vapor somewhere along that line. That's state 1. Now, final state is you're going to heat it. Is the pressure going to go up or the pressure going to go down? It's going to go up. And it's a rigid tank. There's nothing about the change in the mass, so the mass final is equal to the mass initial. There's no change in the mass of the system. The volume final is equal to the volume initial of the tank. Hence, the specific volume, which is defined as the volume divided by the mass initial, is equal to the specific volume final. The specific volume is not going to change because it's a rigid tank. So this is V sub 1. It's also V sub 2. You can conclude that there is state 2, just like that. Make sense? For the propane. So there it is. Now part B, calculate the final temperature in degrees C. Now, tell me about state 2. Subcooled liquid, Superheated vapor. It's superheated vapor. But how am I going to find the temperature at state 2? This is what I would do. I would make a list of state 1 and then state 2. And I would do it like this. I would say, what are all my props? And then make a generic list that doesn't change for a long time in Thermo 1. P, T, V, U, H, S. I know we're not going to use S, but we'll get there. I know that you're new to these properties, but this is what I would do. And then I would say, okay, for state 1, do I know pressure or not? Can I put in a value like 400 kilopascal? Maybe put the units over there. Okay. Let's focus on state 1 for a while. And what else do I know? Well, do I know V? It's because state 1, maybe I should have left more room. Let me do that. Because sometimes it's really helpful if you do this, scoot that up, and say, what describe the state? For state 1, I'm going to describe it as being saturated vapor. And for state 2, superheated vapor. That helps me a lot because now, oh, it's saturated vapor and I know the pressure, 400. Can you get V1? Isn't V1 going to be V sub F? Not V sub F. V sub G? It's going to be V sub G at that 400. Who can look it up? Okay, you have it? V sub G at 400 kilopascal for the 0.1137. And I should have left more room, but it's meters cubed per kilogram. True? How many? Anybody give me a thumbs up? They agree. 1 thumbs up. 2, 3, 4, 5, 6. Good. Guess what? I could get U. I could get H. I could get S. I could get all those properties. All right. Because I need to know U in a second, and you're right there, go ahead and read off U to me. I'm going to need to know U, the internal energy. Can you read that off for me? 418.0 kilojoules per kilogram. All right. And if you wanted to, what is the temperature at state 1? Negative 5.4 something. 6 degrees C. Okay, very good. So I got all these properties. Now over here for state 2, it's superheated vapor. They told me the pressure, 600 kilopascal, true. If I could just get another property, I could get the other properties. What other property can I deduce? V. This is incredible. It's equal to 0.1137. Really? Yep, rigid tank. So V2 is equal to V1. True? So here is one of these things where I have 2 independent intensive properties, pressure, specific volume. Can I now get temperature? Can I find T2 for propane, P-R-O-P-R-A-N-E, at the pressure 600 kPa and the specific volume 0.1137 meters cubed per kilogram? Can I do that? Yeah. How would you do it? Well, we, from our PV diagram, know it's in the superheated region. Go to that pressure block of 600 kPa. I may have these pulled up. So this one was, let me look back here. It started at 400. 400 kPa is 4 bar, isn't it? So that's the temperature. That's our saturated vapor. That's our saturated vapor. So those values are what we picked off. But when we go to the superheated, we're going, this is still 4 bar, 6 bar. True? Don't I go to 6 bar? Now at 6 bar, I need to get that specific volume right. So this was my V, this was my U, this is my H, this is my S column. So I needed at what value, a specific volume? 1137. So I look down here. Doesn't it fall right in here? So right there is 0.1137, somewhere in there. So I could interpolate to get the temperature. How about, you're good at the calculator? How many people have a calculator could do that interpolation in the next 2 minutes? If I gave you 2 minutes, could you do it? I think it'd be good for you to do it. So I like to set up in a separate table. Here's 100, temperature in degrees C. Here's specific volume, meter cube per kilogram. And it's 0.1116, 0.1151, 0.1137. I can't read my own handwriting. 0.1137. 0.1137, yes. 0.1137, and this temperature is 110. Having solved a lot of these problems, I double, triple check to make sure that I'm doing the right interpolation, because I know I made a lot of errors. You have a value? Okay, we have a value of 106. You agree? 106, 2 votes. 3 votes. All right. Well, I think it's 106, okay? Let me jump back to a problem statement. We'll evaluate the work in kilojoules per kilogram. How do I do that? Well, I have a nice sketch of the rigid tank. The focus of the study is the propane inside it. I do a first law analysis that says that the heat in during the process minus the boundary work out equal to the mass times U final minus U initial. Neglect changes in kinetic potential energy. What about this work? It's a rigid tank, no boundary work. So the work is 0, isn't it? That's easy for part C. Evaluate the heat transfer. If I take a look, what are the units they give me for that heat transfer? So they're not asking me to calculate cap Q, but lowercase q 1 to 2, which is cap Q divided by M, so U2 minus U1. So I'll need to get U2. U2 is another linear interpolation, just like we did to get T2. So you interpolate this way to get the U2, and it'll be between 589.2 and 608. And once I have that U2 and U1, boom. That's the answer for part D. Make sense? I'm going to move on then. Sometimes substances are incompressible, not necessarily a refrigerant, but a lot of substances are incompressible. Table A19 gives us some values for selected solids and liquids. Take a look. Aluminum. Let's just focus on aluminum for a second. They tell it at 300 Kelvin. I know if you have high temperature aluminum or low temperature aluminum, you may need to go and get a better source for property values for the aluminum. But around 300 Kelvin, room temperature, close enough. The specific heat of aluminum is given. The density of aluminum is given. Thermal conductivity of aluminum is given, at least in this textbook, in this table. What is this specific heat? Well, it's how the energy content changes with respect to temperature. So the specific heat is, with the constant pressure, is defined as the rate of change of enthalpy with respect to temperature, holding one of the properties constant, pressure constant. That's the definition of specific heat. So you want to find out how much heat goes into the system. Let's say Q in typically is related to a change in H. So that'll be C sub P delta T. How much temperature change was there? What's the value of specific heat? That's how much heat had to come in, or if you know how much heat comes in, that's the temperature rise that you expect. All right. Here's copper. Here are some other brick, common brick, concrete, glass, plate glass. Even some properties for insulating materials, cork, things like that. Now here's some liquids. Go down this way. So ammonia as a liquid at 300 Kelvin. If it's in a liquid state, there's a good value of specific heat, there's a good value of density, there's a good value of thermal conductivity. Here are some mercury, liquid mercury, refrigerants, used engine or unused engine oil, and water. So get familiar with the information that's in the back of the book in the appendices. You can compare data out of table A2 and table A9 to see if the textbook's consistent. So here's water. Here's 300 Kelvin water. If I add 273 Kelvin plus 27 degrees C, what do I get for the absolute temperature? 300 Kelvin, isn't it? So 300 Kelvin is 27 degrees C, right? Well, here's a line out of table A2 for 27 degrees C water. And let's say I just want to check the density value. Well, the density of liquid water or anything is equal to 1 over the specific volume. Here, let's grab this specific volume out and see. 1 over 0.001035. Is that close to 996.5? It should be. And so you can check values. You can do the same thing for refrigerants. So here is refrigerant 134A at 300 Kelvin. You can check that density by going into the table for refrigerant and around 27 degrees C, saturated liquid density calculated. Reciprocate this V sub F, 1 over V sub F for the refrigerant 134A at 27 degrees C, and it should come in close to that reported density. And it will. All right. We already talked about that table, that. Need to talk about ideal gas. Somebody says an ideal gas. What is an ideal gas? It's a substance that is accurately described by the ideal gas equation, which the ideal gas equation is PV is equal to N R bar T. Are we familiar with each of the terms in this equation? So as a quick reminder, what is lowercase n? Number of moles. Typically we use kilomole. R bar, the gas constant, the universal gas constant applied to all ideal gases. We can change that equation if you take and multiply by the number of moles by the molar mass. To be consistent, we'll have to divide R bar by the molar mass, and this equation is still true, isn't it not? But what is the number of moles times the molar mass? The mass. And what is R bar divided by molar mass? R without the bar. And it's the gas constant for the gas of interest. So right away, you look, and it's cap R, but is it with a bar on top or not? If it's with the bar on top, then it's 8.314 kilojoules per kilomole Kelvin. If it's the R without, it depends on the gas. What is the value? It's defined as, R is defined as R bar divided by molar mass of the gas. So this table I wish was in the appendix, but it's not. It's in table 3.1, and they have air, ammonia, argon, carbon dioxide. What they've done is they've taken the molar mass, which they don't repeat in this here table, and they've taken R bar and they divide it by the molar mass, and they've reported R for each of these gases, and you see how the numbers change. And they give it to you both in SI, which we like and use, as well as if you're ever going to use BTUs in pounds, USCS. Here's a reminder. They're just telling you R is R bar divided by, not divided by, yes, it is divided by M. So R is R bar divided by M. And this number, sometimes you'll see me use 0.287. Well, isn't that supposed to be 8.314? No. You divide it by the molar mass of air, which is 28.97, and you'll get that number. There's a couple other variations you should get familiar with. If I take and bring that M over, I'll have V divided by M equal to RT, which is PV equal to RT. Or sometimes PV bar is equal to R bar T. So there's a number of variations. Sometimes I'll put P is equal to rho RT. They're just variations of the same equation. Okay? What's a common mistake? Somebody will be given a temperature like 20 degrees C and they'll put in temperature 20. What do we know? Must be absolute. And the pressure, less common, make sure it's absolute pressure, not gauge. This man, James Prescott Joule, who lived in England in these years, did a number of experiments with ideal gases. In 1845, around that time, he reported some experimental results. It's not that complicated to explain, so let me try and explain it to you. He had a well-insulated water bath, and he could measure the temperature of that water bath very accurately. Let me ask you this. If the water bath changed temperature, it's liquid water, no change of phase, it's a water bath. Can you say something about heat transfer into or out of the water? Could you have a temperature change of the water without a heat transfer in or out of the water bath? You can't. So he's able to look at that thermometer. And if the temperature goes up, there must have been heat transfer into the water. If the temperature goes down, there must have been a heat transfer out of the water. Okay. It's nothing too tricky here. I'm not changing the volume. It's a well-insulated tank of water. Okay. Inside, he has a contraption that has two large volumes on volume A and volume B. And he has a valve that he can remotely open and close. So first he closes the valve and he pulls a vacuum on it, B. Pulls a hard vacuum. There's nothing in it, very little in it. Then on A, he has preloaded some gas. Maybe it's just air. It's at some pressure. So he has this and he lets it sit for a long time. Can you tell me about the temperature of the air when it sits in the water bath for a long time? Will it be the same temperature as the temperature of the water? Sure, it's come into thermal equilibrium. The side B is empty. Side A has an ideal gas, and it could be at a high pressure or low pressure, but there's some amount of ideal gas inside A, and it's at the same temperature as a water bath. What he did was he opened that valve. When he opened the valve, what happens to some of the air in A? It goes into B. True? What do you think the pressure of the gas in A does after a while compared to the pressure of the gas in A initial? Is it the same? It's going to be a lot less, right? It goes down because that gas expanded in volume. But it's a little tricky here, but what he did was he looked hard at that thermometer, and the thermometer did not change value. What did he conclude? There was no heat transfer into or out of the water. The temperature of the water didn't change, true? So what he could do is he could write a first law for the gas. So let's do the first law for the gas. So you'll have that the Q into the gas, this is for the gas, equal minus the work done by the gas equal to the mass times U2 minus U1. And he looked and he said, look, there's no heat transfer to or from the gas to the water because the water temperature didn't change. So that's zero. How did he deduce it? Looked at his thermometer. What about this boundary work? Well, that's also zero. But hold it, it expanded. But what did it push against? Nothing. So it expanded into nothing. Hence, it really did no work. It didn't. So it occupied a larger volume, but that's equal to zero. So the mass didn't change. It stays constant. So what do you conclude about the change in the U? So the U is normally a function of temperature and pressure. But could the U of an ideal gas truly be a function of pressure? The pressure of the ideal gas changed dramatically, but the U didn't change. Hence, he made the observation that the internal energy of the ideal gas is not a function of pressure, it's only a function of temperature. That's a long story. It's not really, I don't think it's in the textbook, but you can read about it in other textbooks or you can read about it on the web. Maybe you missed one of the many steps in the logic, but his bottom line conclusion is that the internal energy is not a function of a temperature and pressure, but only a function of temperature for a true ideal gas. And he repeated that experiment and repeated it and confirmed it and published it, and we still use that today. How do we get this? This is from those experiments. Now, so when you see an ideal gas, you say the equation is always obeyed. Also, from observation, that U is a function of temperature only. And what is the definition of H? Is it U plus PV? Is that enthalpy? Okay. If it's an ideal gas, what is P times V equal to? RT. Okay. If I look at RT, is the product of R times T. What again is R? It's a constant. Is R a function of pressure? It's a constant. No. Is temperature a function of pressure? No, temperature is temperature. It's not a function of pressure. So this is not a function of pressure. It's only a function of temperature. And you add to it something that's a function of temperature only, and you conclude that enthalpy is a function of temperature only as well for an ideal gas. You're less than bewildered, but these are important observations. So 3 things when I say ideal gas come to mind. PV is equal to RT, U is a function of temperature only, and H is a function of temperature only. We have these specific heats. There's 2 specific heats, C sub V and C sub P. One of them is holding pressure constant. Which one is holding pressure constant? C sub P. What about the other one? What's held constant? Volume is constant. Volume. Okay. So the definition of the specific heats, just this is the way they're defined, is that this is the rate of change of internal energy with respect to temperature holding volume constant. This one's the rate of change of enthalpy with respect to temperature holding pressure constant. These are very convenient specific heats, and they're used a lot. So if U is a function of temperature only for an ideal gas, then we can conclude that C sub V is a function of temperature only as well. It can't be a function of temperature and pressure. And likewise, C sub P is a function of, for an ideal gas, is a function of temperature only because H is only a function of temperature. It's as if these partial derivatives become ordinary derivatives. Okay. So a lot of times they'll plot the specific heat. I know this is a funny way of plotting it. C sub P bar divided by R bar. They took it on a molar basis and they divided by the universal gas constant, which would be the same as doing it on a mass basis and dividing by that gas's constant, but either way. And they plotted as a function of temperature. Now, here's Kelvin, and there is 0 Kelvin. What do you know about 0 Kelvin? Super low. Very, very low. Here's 1,000 Kelvin. Do you want somebody to spray 1,000 Kelvin gas on you? No, it's too hot. So right around 300, which would be right around here, is room temperature. And some of these gases, they don't really plot much below 300, maybe below 200, forget it. You can get any gas to condense. You can get helium, you can get liquid nitrogen, liquid helium. You can, it's very hard and expensive, but you can do it. So all in this range, a lot of applications. When you start getting out 2,000 Kelvin and 3,000 Kelvin, it's very, very hot. But what they're showing you is a variation of the specific heat for different gases. Let's take a look at these 2 gases. Don't they show the most dramatic change in the specific heat as they change the temperature? What do you notice about those 2 gases? One is carbon dioxide and one is water vapor. What's the similarity between them compared to these 3 gases and compared to these 3 gases? It takes a while to figure this out, but these have how many molecules or how many components per molecule? 1. These have how many? And these have how many? 3 entities per molecule. So the argon doesn't float around as AR3 or AR2. I always wondered why. Why does argon like that? It just is a loner. Its electrons are happy and they're full shells and they don't want to link up with anybody. No covalent bonding and all that other bonding, right? From chemistry. But oxygen does not like to go around as monoatomic oxygen. It likes to go around as O2. It does not like to go around as O3. No, 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 no. So the oxygen in this room, which is around 20% of what we're breathing, is O2, diatomic. It's happy that way because of the electrons and sharing and okay. But when you put CO2 together, they don't like to go around as CO, and they don't like to go around as C2O or C23O5 or anything crazy. They like to go around as CO2. What's this called? Carbon dioxide. What's this called? Carbon monoxide. Which one's safe to breathe? This is safe. I mean, you don't want to breathe a lot of it. Right now we're probably breathing in this room probably 2,000 ppm. That's my estimate. CO2 in this room is around 2,000 parts per million. So you're inhaling CO2. Guess what? You're inhaling some that I recently exhaled. How's that make you feel? But guess what? I'm inhaling what you recently exhaled too in this room. So that's just what we are doing. But what is this? Carbon. Do you want to breathe a lot of that? What will happen? You will die. It'll clog up your lungs so that you can't get the oxygen, and then you're dead. Okay, so notice, when you have a more complex molecule, you have a more temperature dependence. When you have a simple monoatomic molecule, what's this? It's a straight line. Is it sloped or is it flat? Does the specific heat of argon change as I increase temperature? Does the specific heat of helium change as I increase temperature? What's that other one? Ne. Neon. It's a noble gas. So they don't like to participate. And the way they float around on a molecular level, the way they have energy, if you go to higher temperature, they can just move faster in a straight line. Where if you got these other molecules, you think about how they have energy in a molecular level, they can move fast, but they can also sit there and vibrate. And they can also tumble. So they can have energy in a translational mode, in a vibrational mode, and also in a rotational mode. They're more complex, hence they have more temperature-dependent specific heats. These are very simple, only in a translational. When you have two, well, you can have some dumbbell, but you don't have as many dynamic in vibration modes. So, but they're still temperature-dependent. All right. I will get asked this question always when I teach like Thermo 2. It's like, I can't get the specific heat for argon. Well, this number right here, they even tell it to you, it's 2.5, okay, which is 5 halves. That's 5 halves right there. It's so if I wanted the C sub P of argon, it's 5 halves times R. I don't need a table to get it. I pick it off of this figure. So it's 5 halves R bar divided by the molar mass of that argon or helium if it's one of these monoatomic gases. Okay. If you wanted to fit a polynomial to that temperature-dependent specific heats, you don't need to do it. Somebody already did. So here's the alpha, the beta, the gamma, the delta, the epsilon that go to this temperature-dependent polynomial for a good fit. So all these gases, there's the coefficients. Couple things to mention. What is the range of the temperatures for this polynomial fit? It's in Kelvin only from 300 to 1,000. Have you ever plotted a polynomial curve fit and then extrapolated? What does it look like? It's like number one rule coming out of numerical methods when you curve fit a polynomial is that you don't use it to extrapolate. Because often the thing is nice and well behaved and catches some slopes in here, but then this is the range in which you fit it, but then it quickly goes like crazy outside. You don't use it to extrapolate. So you have to be very careful not to use it at, let's say I want to do it from 1,000 to 2,000 Kelvin. Don't use it. Be very sensitive or careful with that temperature range. Also, if you take a look at down here, you want to read sometimes the fine print. Monoatomic gases, 2.5, 0, 0, 0, 0. That's just what we talked about. And monoatomic gases such as helium, neon, argon. So over a wide range of temperatures, nearly 5/2 R bar. Air tables. So here's a whole table for air. In a way, I wish they hadn't given us this air table. I've seen so many students just make mistakes in the air tables. But it's there. The textbook uses it to solve a lot of example problems. You can use it on exams, but be careful. So here's temperature in Kelvin. And right over here, guess what? To save space, and this is one of the worst things they did, is they should have just left a lot of white space, in my opinion. Some textbooks do that. But so this temperature, let's say, what's that, 290? This is all for 290. Stop. Maybe they should have put a big black bold line. Stop, 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 stop. Maybe in your table you draw a big, thick black line so that you know that, oh, if I need it at 500, there it is. But if I come over here, 290, sometimes students will grab numbers way over here. Maybe that's just a reflection that they didn't solve enough homework problems. Maybe. Okay, do you see that? So if you wanted to know the enthalpy, internal energy, don't worry about this S naught and do not worry about this two columns. All of this, don't worry about it. You have to get the entropy. We'll get to it later. But for right now, enthalpy and internal energy values you can get very accurately for air out of the tables. You can also get it for different gases. Carbon dioxide, carbon monoxide, water vapor, oxygen. But notice they have an H bar and a U bar. Don't worry about the S naughts. What does that bar on top of the H mean? It's per amount per kilomole, not per kilogram. So H units were kilojoules per kilogram. H bar, kilojoules per kilomole. You can see it right up in here. Look at here, right here. They're saying these are the units for H bar and U bar in kilojoules per kilomole. Right there, key piece of information. Somebody says, I have an ideal gas that undergoes a polytropic process such that P times V to the 1.2 is equal to a constant. Is it also true that PV equals MRT during the same polytropic process? Or is it impossible for both of these to be true during the same process? Is it, I have it worded kind of roughly, but let me ask you, can both be true during the same process? Yes or no?
Yes.
Tough question. It is yes. And why can it be yes?
It's a characteristic of an ideal gas.
Because I'm changing T as I'm going along. T is what's allowing me to work it. Okay? It's true that this is always true, but just because what I'm doing is I'm changing T such that it forces some, fit to work on the exponent on V. Does that make sense? All right. Just because it's an ideal gas doesn't mean it cannot undergo a polytropic process. Actually, a lot of ideal gases we compress rapidly and they behave perfectly as a ideal gas while we're compressing, and it is a polytropic compression or expansion process. No time. That was to get the property values out of this table. Last concept before we move on. Sometimes they don't behave as pure, perfect ideal gases. PV is equal to RT as a gas. And what they'll say is, most of the time, PV divided by RT is perfectly equal to 1, and it behaves as an ideal gas. But sometimes they compute PV is equal to RT, and it's not equal to 1. And so they'll say, well, it's equal to Z, whatever Z is. Z is the compressibility factor. When Z is close to 1, we say it's ideal gas. And when it starts to get far away from 1, we say we shouldn't use the ideal gas equation anymore. So that's what the compressibility factor Z is. It's a ratio PV divided by RT. Here's a chart of the compressibility factor. What's on the y-axis? Z. When Z is close to 1, it behaves as an ideal gas. As an engineer, you'd say, well, in this region right here, everything that's in that region right there that's close to 1, it behaves as an ideal gas. Well, what do they plot for a number of different gases? Methane, ethylene, ethane, propane, isopentane, nitrogen, carbon dioxide, water vapor. They plot different data points. They plot it as a function of the reduced pressure. The reduced pressure, P sub R, is the actual pressure divided by P sub C for that substance, for that gas. What is C, P sub C? Critical. Yeah, it's a critical pressure, critical point pressure. And then T sub R, guess what that's defined as? The actual temperature divided by the critical point temperature. So if you're thinking about that dome, and you could put it on a PV diagram or a TV diagram. There's a number of diagrams. If I have the ratio of 2, T sub R is 2, you could see that for a lot of them, if T sub R is in the vicinity of 2 or greater, that means the temperature is about twice the critical point temperature. It behaves as an ideal gas. It's warm compared to the dome, the critical point temperature. Also, if I go to very low pressures, what happens at low pressures? Everything's converging to 1. So at low pressures, meaning that the actual pressure is low compared to the critical point pressure, then it behaves as an ideal gas. So at low pressures, high temperatures, gases behave as ideal gases. When you start getting low temperatures near the critical point, high pressures that are above the critical point, things behave as real gases and they deviate from the ideal gas. You can get a compressibility factor much different than 1. If you want to zoom into that region, here's a zoom in, and that's in the appendix. All right. Let me go ahead and stop and give you a little quiz for today.